Okay, we're starting chapter 5, and chapter 5 is all about the gaseous state. We will be talking about the gas laws, we will talk about units of pressure, we'll talk about gas stoichiometry. We'll cover the whole gamut of lots of different things. I'll be showing you a lot of problems and the solutions to those problems. First things first, though, we need to define what pressure is and talk about the units of pressure, because when we're talking about gases, we'll be talking about the temperature of the gas, the volume of the gas, and we also will be talking about the pressure of the gas. What is pressure? Pressure, here's the definition, is the force exerted per unit area of surface by molecules in motion. So when your gas molecules are in motion in a container and they're hitting the side of the container, that is pressure, okay? What are the units of pressure? Well, the one that you may have already heard about is ATM, which stands for atmosphere. There's millimeters of mercury, because when we measure with a barometer, the barometer is always used, or at least the original barometers before they went all digital, they used to have mercury in the original barometers. So millimeters of mercury, how high up the mercury went up into the barometer. We also use units of torr. We use units of pascals or kilopascals. We use units of PSI. Okay, so these are the typical units that you will be seeing. I think that's pretty much it that you'll be seeing. Okay, so we need to be able to convert from one unit to another. You should know that 1 atmosphere is equal to 760 millimeters of mercury. Okay, you should know that 1 atmosphere is also equal to 760 torr. So a torr is a millimeter of mercury. You should know that 1 atmosphere is equal to 101,325 pascals. Ridiculously huge number. So a lot of times we'll just use kilopascal. So 1 atmosphere is equal to 101.325 kilopascals. And then finally, 1 atmosphere is equal to 14.7 pounds per square inch, or PSI. Okay, so you should know these conversions and be able to, if I give you atmosphere, convert it to millimeters of mercury. If I give you torr, be able to convert it to pascals, go back and forth, create conversion factors with these. It shouldn't be too difficult at all. Okay, so we're going to go ahead and get started with the gas laws, and you probably remember the basic gas laws from intro chemistry. You've got Boyle's, Charles, combined gas law, ideal gas law. Do you remember all of those? Okay, so let's first start off with Boyle's. What is Boyle's law? Well, Boyle's law states that at constant temperature, the pressure of a gas and the volume of a gas are inversely proportional. So if you increase the volume, the pressure decreases within that, the pressure of the gas decreases. If you decrease the volume, basically you squish all the gas molecules into a really small volume, the pressure inside that container increases. So you should know that at constant temperature, the pressure and volume of a gas are inversely proportional. What does inversely proportional mean? It just means that as one goes up, the other one goes down. So, like I said, as the volume goes up, the pressure goes down. As the volume goes down, the pressure goes up. Okay, so what is the actual gas law? That one is P1 V1 equals to P2 V2. Initial pressure, initial volume, it sort of looks like the dilution one a little bit, but now here we're dealing with gases. So initial pressure, initial volume, final pressure, final volume. So if you are changing the volume, the pressure will change also. If you're making the volume bigger, the pressure will go down. All right, it's pretty straightforward. It's plug and chug. What units do you have to use? You could use any units, provided that the units of pressure on this side and this side are both the same. So if you're going to use torr over here, you're going to use torr over here. If you're going to use atmospheres here, use atmospheres here. What about the volume? Doesn't matter what the units are. Milliliters here, milliliters here. Liters here, liters here. It does not matter, but they have to be the same so that everything can cancel. Okay, so really easy one. Let's go ahead and do one. Volume of oxygen gas. Oh, and here's another thing. Maybe I should tell you this before we get started with problems. When we're doing the kinetic molecular theory, and you're going to find out that basically we consider that the gas particles themselves are negligible. So how do we figure out the volume of a gas? The volume of the gas is the container, the volume of the container that the gas is in. So I'll tell you, oxygen was in a 25 ml container. That means the volume of the gas is 25 mils. Because what happens is that when a gas gets into a container, it just pretty much fills out the container. If it's a huge container, then there's more space between the gas molecules. If it's a small container, they're more squished together. So you take all those gas molecules that are in this room and then squish them into a tiny little bottle. Let's say I put them in here. I could, if I could like shut off this room, I could squish all the gas molecules that are in this room and put them into this. So now the volume of the gas would be this Coke Zero bottle. And I don't even know how many milliliters this is. Does anyone know that? I've been drinking it and I don't even know. Anyway, bottom line is, and I can't even see it. It doesn't matter. But it's because I don't want to give the English units, I wanted the metric units. And for the life of me, I can't see it. Doesn't matter. But you get the idea. The volume of the gas is the volume of the container that it is in. All right? So you haven't changed the quantity of the gas when you change the volume. Like let's say you had 1 million gas molecules, and there's way more, in this room. You squish them into a small bottle, there's still 1 million gas molecules, but their volume is smaller. And when the volume goes down, now the pressure goes up because they're all squished into that bottle and they're just pounding the side of the bottle like crazy. All right, so enough of that. Let's talk about an actual problem. All right, you have the volume of oxygen gas occupies 38.7 milliliters. So V1 is equal to 38.7 milliliters. And at a pressure of 751 millimeters of mercury. So pressure is 751 millimeters of mercury. Okay, and 21 degrees Celsius. What is the volume if the pressure changes to 359 millimeters of mercury while the temperature remains constant? Remember, with Boyle's law, the temperature has to remain constant. So we are, they're asking you, what is the new volume? So V2 is what we don't know. And then P2, we're changing the pressure. Instead of it being 751 millimeters of mercury, it is now 359 millimeters of mercury. So without doing any math, just look at it. What have you done to the pressure? It's gone from 751 down to 359. So what do you expect to happen to the volume? If you reduce the pressure, that means the volume must have increased. So your final answer has to be more than 38.7. You plug in the numbers over here. So we're going to put 700, put 751 over here, and 38.7 is equal to, P2 is 359, and then this is your unknown, X is V2. And you get your calculator, and it's 751. Again, these are such easy problems. 751 times 38.7 divided by 359, and you get 80.9573, etc., etc. But how many sig figs do we want? We want 3 sig figs. So since after the 9 there's a 5, so we have to round up. So your final answer would be 81.0 milliliters. Why milliliters? Because I used milliliters here, so this must be milliliters. Okay? Easy enough. That is Boyle's law. What about Charles' law? What is that? Well, Charles' law is the relationship between volume and temperature, with pressure held constant. Okay? So Charles, this is the pressure is held constant. And what basically this says is that volume and Kelvin, it has to be Kelvin, not Celsius, volume and Kelvin temperature are directly proportional. Directly proportional, meaning as the temperature goes up, volume goes up. As the temperature goes down, volume goes down. And the temperature must, and I repeat, must be in Kelvin. With every single gas law problem you do, if temperature is involved, you must convert your Celsius temperature to Kelvin. How do you do that? You remember that from chapter 1? You take your degrees Celsius, you add 273, and then it gives you your Kelvin, okay? So here's a quick question. Oh, let me show you what the actual equation is. So it's V1 over T1 is equal to V2 over T2. That's Charles' law, all right? So V1 is initial volume, T1 is initial Kelvin temperature. V2 is final volume, T2 is final Kelvin temperature, okay? All right, so the question is, you prepared carbon dioxide by adding hydrochloric acid to calcium carbonate, blah, blah, blah. According to your calculations, you should obtain 79.4 milliliters of carbon dioxide at 0 degrees Celsius and 760 millimeters of mercury. How many milliliters of gas would you obtain at 27? So basically, they're telling you at the initial volume and the initial temperature, at the initial temperature of 0 degrees Celsius, with this reaction, you're going to get 79.4 milliliters of carbon dioxide when you run that reaction, okay? Now the pressure is going to remain constant, so they put the pressure there, but you're not using it for this because the only thing that's changing is the volume and the temperature. And they're asking you, how many milliliters of gas would you obtain at 27 degrees Celsius? So now we have, this is going to be 27 degrees Celsius, and they want to know what V2 is. Okay, before we plug in any numbers, take a look and see what happened to the temperature. It went from 0 degrees to 27 degrees. Did the temperature go up or down? It went up. So that means the volume will go up. Now, before we plug any numbers in, you must convert your Celsius to Kelvin. Please don't forget that. So we're going to add 273 to this. So that's 273 Kelvin. So T1, let's see, hopefully you can see this, is 273 Kelvin. T2, we're going to add 273 to this. And here's 10, 300 Kelvin. Okay, so it's going from 273 Kelvin to 300 Kelvin. Let's plug in the numbers and see what we get. All right, I'm going to go ahead and erase this so we can do the math. All right, so V1 is 79.4 milliliters. T1 is 273 Kelvin. V2 is my X, that's my unknown. And then T2 is the 300 Kelvin, okay? So manipulate the equation, bring this over here, and then that way your Kelvins will cancel. So 79.4 times 300, because you're bringing it over here, and then divide by 273, and that will give you that X. So let's go ahead and do that. 79.4 times 300 divided by 273, and you get 87.5824, etc., etc. We only need 3 sig figs, so it would be 87.6 milliliters. So when you increase the temperature, let's see if I did this right. Hopefully I did it right. Oh, let's see here. Hold on 1 second, guys. So 300 times 79.4 divided by 273, 87.3. Why did I write 87.6? I have no idea. Sorry about that. All right, good. I'm glad I caught it fast enough. It says 87.252. I'm just rounding it up to 87.3. Okay, we're good. Okay, all right. Next one, we will be doing the combined gas law.